In a 100-meter dash, detailed video analysis indicated that a particular sprinter's speed can be modeled as a quadratic function of time at the beginning of a race, reaching a speed of 12.1 meters per second in 1.7 seconds, and then as a linear function of time for the remainder of the race. She finished the race in 10.6 seconds. So event 1 is when the race begins, and event 3 is when she finishes the race, which she does in 10.6 seconds. So if t1 is equal to 0, t3 is 10.6. The speed changes from being modeled as a quadratic function of time to being modeled as a linear function of time at 1.7 seconds. Let's just say event 2 is at 1.7 seconds. And let's say position 1 is equal to 0, since it's a 100-meter dash. Position 3 is equal to 100 meters. She is supposed to begin the race at rest, so velocity 1 should be equal to 0. At 1.7 seconds, the velocity is 12.1 meters per second. I think that is everything that I can put in the table from reading over the problem. We know that initially the speed can be modeled as a quadratic function of time, but remember, from the footnote on page 6, quadratic does not mean at squared plus bt plus c. It means at squared plus b. So there is no t term in our quadratic function for speed. So as we go from event 1 to event 2, the velocity can be modeled as at squared plus b. That would look like this if I draw a velocity versus time graph like that. Okay, first I want to find the constants a and b. Make sure that you use a capital A for your constant so that you don't confuse it with the little a, which is acceleration. Okay, so a and b are just some constants. We are going to figure out what these constants are. We can do this by using the numbers in our table. So looking at what we have when t is equal to 0, so the velocity when t is equal to 0 is 0, because I said she should start at rest if it's a race. And if I put 0 in for time, a times t squared is 0, so this is 0 plus b, but it's supposed to be equal to 0, therefore b must be equal to 0. My other initial condition that I have is that the position when the race begins is 0, but I can't use that with my velocity versus time graph. I would have to integrate in order to use that information. So I can also use this equation is good all the way from when t is equal to 0 to when t is equal to 1.7 seconds. So I can also use when t is equal to 1.7 seconds, I have a times 1.7 seconds squared plus b, but now I know that b is equal to 0, so I'm just going to leave that off. And this is supposed to be equal to 12.1 meters per second. So this is 12.1 meters per second. Therefore, a is equal to 12.1 meters per second divided by 1.7 seconds squared. And for that, I get 4.19 meters per second cubed. 4.19 meters per second cubed. So now if I go back to my equation here and put in a and b, I have the velocity as a function of time is equal to 4.19 meters per second cubed times t squared plus 0 for b. Okay, so that when you put in time in seconds, you have seconds squared. That cancels out with 2 of the seconds in the denominator, leaving you with units of meters per second for the velocity. Okay, so the units all work out. You don't have to include them as you do all your calculations, as long as everything in your table here has units. So now I have my equation for velocity, but I already know velocity 1 and velocity 2. So in order to use this equation, I can take the derivative in order to find the acceleration, and I can integrate in order to find an equation for the position. So I'll next find the acceleration. Okay, so I started off by finding the constants a and b. Now I'm going to find the acceleration, and I remember that the acceleration is the derivative of the velocity with respect to time. Taking the derivative of what I have here, and let's leave off the units now. So if I take the derivative of 4.19 times t squared, it's 2 times 4.19 times t. And this tells me the acceleration when t is equal to 0. If I plug in 0 for t here, I get 0, so I can put that in my table. And I can also find the acceleration at event 2 using my equation here. When t is equal to 1.7 seconds, I get 2 times 4.19 times 1.7. And I have to put in the units myself because I left them off here. If I kept the meters per second cubed, and then that would be here for the 4.19 meters per second cubed times time in seconds, that would give me acceleration in meters per second squared. So that would all work out. And this is 14.2. Now you can put the units back in and put that up in your table. Meters per second squared. Okay, now I have to find position 2. In order to find the position, I integrate. So the position as a function of time is equal to the integral of the velocity as a function of time with respect to t. I'm not putting in limits of integration, so this is indefinite integration. So when I integrate, I need to remember to add the constant of integration. Okay, so I'm going to take my equation here for velocity and put it in. So this is 4.19 t squared integrated with respect to t. So I raised the power, so it's 4.19 times t cubed, and dividing by the new power, which is 3, gives me 4.19 divided by 3 times t cubed plus a constant. I haven't used c yet, I used a and b here, so let's just say c for the constant. Okay, then I have to figure out what that constant is. Well, this is easy because I know that the initial position is equal to 0. So the position when time is equal to 0 is supposed to be equal to 0. Putting in 0 for the time there would give me 0 plus c, but this is supposed to be equal to 0, therefore c is equal to 0, and that I got from using my position here. So then the other thing I can do is look at my equation here when time is equal to 1.7 seconds to find R2. So when time is equal to 1.7 seconds, I have 4.19 divided by 3 times 1.7 cubed, and that gives me 6.86. And I know that's supposed to be in meters. If I kept the units in, it would turn out to be in meters. Okay, so that is going from event 1 to event 2, and we're going to stop here, and then part 2 of this will resume with going from event 2 to event 3.